This is Algebra 3, Prerequisite Chapter, Section 2, Exponents and Radicals. First, we're going to talk about integer exponents. Repeated multiplication can be written in exponent form. This should not be a surprise. This is nothing new. Some examples of how that works. Note specifically the -4 that is being multiplied by itself there. In the notation, the negative is inside the parentheses with the 4 and the power is on the outside. This is very important, especially if you intend to use your calculator to figure out what -4 to the third is. If you do not put the parentheses around the -4, it will be wrong. It will not give you the right answer. Just a couple of terms. If you look at the notation there, we have a to the n. N is called the exponent. That's how many times you're going to be multiplying that number by itself. And a, the number you're multiplying, or the variable, is called the base. And you read this as a to the nth power. You can also have a negative exponent. Okay, here are a few of the properties of exponents. Again, you have seen these since Algebra 1, so these should not be anything new to you. Just look through the various properties. Hopefully this will just be a refresher for you. You've got the multiplication, division. The one that people tend to forget is the negative one. That's one that you probably just had last year in Algebra 2. When you raise a number to a negative power, what that does is it takes the reciprocal of that number. So for example, 2 to the -4 power would be 1 over 2 to the 4th. Rule number 4 is another one that's very commonly missed. A to the 0 is 1. Anything to the 0 power is 1 except 0. 0 to the 0 power is undefined. Go ahead and look through the rest of these. If you need a moment to think about them and to read them, pause the recording and then resume when you're ready to move on. Again, I'm bringing up the point here about the difference between -2 in parentheses to the 4th and -2 to the 4th with no parentheses. Notice the difference. The parentheses indicate the exponent applies to the negative sign as well as the number. But without the parentheses, the exponent only applies to the 2. So in the example there, you can see the difference. If you try it on your calculator both ways, you will see the difference. Here are a few examples for you to practice to simplify your exponents. Why don't you pause the recording, try each of these, and then resume the recording to check your answers. The answers are across the bottom of your screen. A is -12, a squared b. The -12 should be obvious. A times a is a squared. B to the 4th times b to the -3rd, you're going to add those powers. Problem B, everything in there gets the third power. It's going to be 2 to the 3rd, x to the 3rd, and y squared to the 3rd. 2 to the 3rd is 8, x to the 3rd is x to the 3rd. Y squared to the 3rd, when you raise a power to a power, you're going to multiply those powers. So that's where we get the y to the 6th. In problem C, that -4a squared is in parentheses with a 0 power on it. So that whole thing becomes 1, and your answer is simply 3a. And then in D, here's another example of giving the power on the outside of the parentheses to everything inside. So 5 squared, x to the 3rd squared, and y squared. That gives us 25, x to the 6th over y squared. Exponents are a great way to write very large numbers or very small numbers. There's an example. There's 359 billion gallons of water, and you see the number written out there. It's much easier to write it using scientific notation, which you see at the bottom of the notes, 3.59 times 10 to the 20th. With scientific notation, the decimal goes after the first number. So it goes after the 3.59. The first number in scientific notation is never going to be larger than 10. In fact, it can't be 10. So the number has to be between 1, and it can be 1, but less than 10. The positive exponent 20 indicates the number is large. So when you have a positive exponent, you're going to have a very large number. The decimal will be moved 20 places to the right to convert from scientific notation to regular notation. A negative exponent indicates that you have a number that is very small. And when you convert from scientific notation to regular notation with a negative power, you're going to move the decimal that many places to the left. Here's an example. The mass of one electron is 9.0 times 10 to the negative 28. In order to change this to the regular number, we're going to move the decimal from the 9 28 places. Very small number. Here's an example. You need to use scientific notation to evaluate this. Try this problem for yourself, pause the recording, give it a try, and then resume recording for the answer. What you're supposed to do is rewrite the numbers in scientific notation. The reason for this is that it gives you smaller numbers to multiply, and you can use the properties of exponents with the tens, the powers of 10. So first thing they did was they changed everything to scientific notation, and then they combined the powers of 10 on top and on the bottom, and then finally multiplied the 2.4 times 4.5. Actually, you just can cancel the 4.5s, and that leaves you with 2.4. 10 to the third over 10 to the minus 2. Remember your rules. When you're dividing the same number, you subtract the powers. 3 minus negative 2 is 5. So the answer is 2.4 times 10 to the fifth, which is 240,000. The square root of a number is one of its two equal factors. For example, 5 is a square root of 25 because 5 times 5 is 25. A cube root is a number is one of its three equal factors. For example, the cube root of 125 is 5 because 5 times 5 times 5 is 125. We have a definition of an nth root. Let a and b be real numbers, and let n be greater than or equal to 2, and it's a positive integer. If a equals b to the n, then b is the nth root of a. When n is 2, the root is a square root. When n is 3, the root is a cube root. So in other words, if n is 4, if a is b to the fourth, then b is the fourth root of a. And some numbers do have more than one nth root. For example, both 5 and negative 5 are square roots of 25. You've heard this before. The principal square root of 25 is just 5. So when they just give you the square root of 25 and ask you to find the square root, all they want is the positive number. They want the principal square root. If they want the negative, they will put the negative on there. Now what can become confusing later on is when we are solving equations and we have to take a root, then we actually do have to put the plus or minus on front. But we only do that when we are solving an equation for a variable and taking a square root to do that. Okay, the principal root of the number is the positive root of that number. And you're only going to have this concern with even roots, 2, 4, 6, and so on. This is a little bit more of what we're talking about. The square root sign itself does not imply both negative and positive, only the positive. So this is really just a reiteration of what we just said. If you look down at the bottom, integers such as 1, 4, 9, 16, 25, and 36 are called perfect squares. Why? Because they have integer square roots. 1 times 1 is 1, 2 times 2 is 4, and so on. Similarly, integers such as 1, 8, 27, 64, and 125 are called perfect cubes because they have integer cube roots. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27. And here's some more properties. These are generalizations about the nth root of real numbers. By the way, the reason they're using n and not a specific number there is because this applies to any number n. And if they used a specific number, the idea would be it would only apply to that number. So n can actually represent pretty much any number. Okay, looking at this chart, they actually give you a number example at the end. Those are kind of handy to look at. So if your number a is positive and n, which is going to be the number in the root, if that's even, then there are actually two roots. There's a positive and a negative. So if your root is even, if it's a square root of fourth root, a sixth root, etc., you do have two roots. The principal root is always the positive. All right, if a is positive or negative, so the number under the radical, under the root symbol is positive or negative, and your root is odd, then you're going to have one root, and it's just the root of that number. For example, the cube root of -8 is -2. It is perfectly fine to have negative numbers under odd roots. Just think about it. -2 times -2 times -2. That is -8. Even numbers, well, that comes next. If a is less than 0 and n is even, so this time we have an even root, you don't have a real root. And the example they give is the square root of -4. You cannot come up with a real number that multiplied by itself gives you -4, because -2 times -2 is +4. So the square root or the even root of a negative number is not a real number. That there is no real root there. If a is 0 and your root is even or odd, the answer is 0. In other words, any root of 0 is 0, which makes sense. Okay, we have properties of radicals now. We went from talking about exponents near the beginning to radicals. And you'll notice these properties are very similar. Our first property says that if you're taking a root and you're doing a power at the same time, it really doesn't matter which order you do it in. You can do the power first and then take the root, or you can do the root first and take the power. And which is better really depends on the problem itself. The example they give is the cube root of 8 squared. Well, 8 happens to have a cube root, it's 2. So it might be easier to do the cube root first and get 2 and then square that and get 4. Or you could square the 8 and get 64 and then do the cube root of that. You'll get the same answer either way. And again, which way you do often just depends on which is easier. Number 2 tells us that if we have two things multiplied together and they're under the same root, then you can just bring them together under one symbol and multiply them. So the square root of 5 times the square root of 7 is the square root of 35. Property 3 allows us to do the same thing with division as long as we don't have a 0 denominator. Property 4 says if you're taking a root of a root, that you actually multiply those two together. So the cube root of the square root of 10 is the 6th root of 10. That just sounds really, really familiar. These are very similar to the exponent properties, and there's a reason for that. But we'll get to that later. Number 5, when you have an nth root and you raise it to the nth power, the root and the power cancel, and you're just left with the number. The square root of 3 squared is 3. And then it makes this comment too, you've got to be careful. For if n is even, when you do this, what we just did above, you get the absolute value. So the square root of -12 squared is not -12, it's +12. If it's an odd root, then you just keep the sign. But if it's even, you want to go with the positive. Okay, let's try these examples. We're going to use the properties of radicals to simplify each expression. Pause this recording, try the problem yourself, and then resume the recording to check your answers. All right, for A, we should have gotten 4. For B, 5. C is X. And D is the absolute value of Y. Now, the reason we're putting the absolute value there is we really don't know if Y was positive or negative since it's a Y and not a number. So you want to put the absolute value there. Okay. Now, simplifying radicals. An expression involving radicals is in simplest form when the following conditions are satisfied. All possible factors have been removed from the radical. In other words, you cannot pull anything else out of that radical than you have already done. All fractions have a radical-free denominator. And to accomplish that, we have to do a process called rationalizing the denominator. And the index of the radical is reduced. In other words, if that number outside the root symbol can be reduced, you've reduced it. To simplify a radical, factor the radicand, that's the number under the root, into prime factors, and then find groups of identical numbers that match the index. The index is the number on the root. So if it's a square root, you're going to find pairs. If it's a cube root, you're going to do groups of 3. Group numbers, numbers that had a partner, get to leave the radical and they go outside. Ungrouped numbers get multiplied back together and they stay inside the radical. Here are a few examples. Give these a try and then check your answers. For A, we have 2 cube roots of 3. 24 is 8 times 3. 8 is 2 times 2 times 2, so we have 3 2's. The cube root, we have a group of 3 2's. The 2's get to come out. The 3 didn't have a date. It has to stay at home under the radical. We did the same thing with 48. If you break down 48, you're going to get 2 times 2 times 2 times 2, that's 4 2's, times 3. That group of 4 2's gets to come out. And notice we only write it down one time for the entire group. The 3 didn't have anybody to come out with, so it has to stay under the radical. C shows us we can even do the same thing with variables. 75 breaks down to 5 times 5 times 3. It's a square root, so the 2 5's get to come out. We write it down one time. The 3 stays underneath. But what about the x's? Well, we're looking for groups of 2, and we have 3 x's. So 2 of the x's get to come out. We write them down one time. The remaining x stays underneath. D, again, same idea. In fact, D and A are very similar. We're working with the cube root of 24 again. So the 2 and the 3 are in the same positions as in A, in example A. The letter A, it's A to the 4th. That's 4 A's. So the 3 get to come out. We write it down one time, and the 1 stays underneath. And then notice for E, 5 absolute value of x. Now the 5 is a number, and we know it's positive to start with, so we leave it 5. But we don't know what x is. We don't know if it's going to be positive or negative, so we want to make it clear that x needs to be positive and show the absolute value. Okay, a little bit more about simplifying radicals. Radical expressions can be combined, added, or subtracted when they are like radicals, kind of like terms. What that means is they have the same index and the same radicand. In other words, it's the same type of root, a square root, a cube root, whatever, and the number in the root has to be the same. For example, square root of 2, 3 square root of 2, 1/2 square root of 2, those are like. Square root of 2 and square root of 3 are not. To determine whether you can combine them, you need to simplify them first, because sometimes they'll give them to you unsimplified, and once you simplify them, you realize they really are like, even though they didn't look like it from the start. All right, we have a couple of examples here. Give these a try, pause, and then when you have your answer, resume and check them. Okay, the answers are pretty well worked out here, so you can see how we arrived at both final solutions. I will pause a moment and look over that, see if you got the answer right, and if not, see if you could figure out what happened. Rationalizing the denominator is a very important concept, something that we need to use and will use a lot. So it's really important that we get a hold of this. We don't want to leave a square root or any root actually in the denominator of a fraction. Now, if the denominator, and you can rationalize the numerator too. So the same principle would apply if they want you to rationalize the numerator. Although to be honest, it's far more common to rationalize the denominator. If it has the form a minus b squared to m, or a plus b times the square root of m, then what you're going to do is multiply the numerator and denominator by the conjugate. And what the conjugate is, it's the same exact thing with the opposite sign. So in other words, a plus b squared of m and a minus b squared of m are conjugates of each other. 2 plus the square root of 3, 2 minus the square root of 3. 5 plus the square root of 7, 5 minus the square root of 7. When you multiply them together, and be sure to use FOIL, what will happen is that the square roots will actually cancel each other out, and that takes care of the problem. Now, if you don't have an a, if it's not something plus or minus a square root, if it's just a square root, then just multiply the top and the bottom by that square root. Now for cube roots or higher roots, it's a little bit more complicated because remember, in order to get rid of a cube root, in order to pull something out from it, you have to have 3 factors. So if you have the cube root of 2 in the denominator, you will actually need to multiply by the cube root of 2 times 2, or 4. Because 2 times 4 is 8, the cube root of 8 is 2. You need the 3 2's, the 2 that you started with, and the 2 times 2, which made 4. You need all 3 of those together in order to make the cube root go away. All right, another example. I believe our final example. You need to rationalize the denominator of each expression. Give it a try. Pause the recording. Resume when you're ready to check your answers. Okay, here are 3 answers. On A, you needed to multiply the numerator and denominator by the square root of 3. So on the bottom, you have 2 times the square root of 3 times the square root of 3, or 2 times the square root of 9. Well, the square root of 9 is 3, so it's 2 times 3, which is 6. On the top, you'll have 5 square root of 3. Remember, whatever you do to the denominator, as far as multiplying goes, you have to do the same thing to the numerator. Otherwise, you're changing the value of the fraction. And we don't want to change the value, just the way it looks. B is an example of a cube root. So what I need to multiply the denominator by is the cube root of 5 times 5, or 25. What that will do is it'll give me the cube root of 125 in the denominator, which simplifies to 5. I also have to multiply the top by the cube root of 25, so the top is going to be 2 times the cube root of 25. Part C is one of the more complicated ones where you have to multiply by a conjugate. We have 3 plus the square root of 7. We need to multiply by 3 minus the square root of 7. When you do that to the denominator, you're going to FOIL it out. When you FOIL it, that gives you 9 plus 3 square root of 7 minus 3 square root of 7. Those are going to go away. Minus the square root of 49, which is 7. So on the bottom, you're going to have 9 minus 7, which is 2. Now remember, we're also multiplying the top by 3 minus the square root of 7. Well, the top already has a 2, so the 2 on the top and the 2 on the bottom cancel and leave you with 3 minus the square root of 7. Now, we can also look at roots as being actually powers. We can write them as powers. And what they're going to look like is they're going to look like fractions. So, for example, a square root is actually a 1/2 power. A cube root is actually a 1/3 power. And it gets even more interesting because if you have not just a root, but also power, like you're doing the square root of 3 to the 3rd, well, you can take the root and the power and write them together as a fraction. The square root of 3 to the 3rd would be 3 to the 3/2 power. Okay, the numerator of a fractional exponent tells you what power you're going to raise the base to. The denominator is the index or the root. It tells you what root you're going to take. So in the example at the bottom, b to the m over n, m is the power, n is the root. Top is the power, bottom is the root. Now, all the rules that we learned for integer exponents, they all still work. We don't need to go back and learn new rules. So if you're multiplying 2 to the 1/2 times 2 to the 1/3, when you multiply the same number together, you add the powers. 1/2 plus 1/3 gives you 5/6. You can also use these fractional powers to do roots on your calculator. So instead of going into the menu and trying to do a root, like let's say you want to take the 5th root of something, then what you can do instead is to type the power key and then put 1/5. So it actually makes it easier. If you go on to calculus, that's another instance where it is much easier to deal with roots as powers, much easier to simplify expressions that way. And here's some more examples using our radical properties and the fractional exponents. Pause this recording, try the problems, and then resume your recording to check your answers. Here are our answers. -32 to the -4/5 is 1/16. Remember that negative power flips it upside down. It's a positive answer because we're raising a negative number to an even power, the 4th power. The 5th root of 32 is 2. 2 to the 4th is 16. B, a little bit easier. We're going to multiply the -5 times the 3 and get -15. Then we're going to add the powers on the x's. So 5/3 plus -3/4, and we're going to come up with 11/12. On letter C, we really make this easy by writing the root and the power as a fraction. In other words, the 9th root of a to the 3rd is a to the 3/9 power. Now reduce it. Reduce 3/9 just like you would if it was just a regular old fraction. That gives you a to the 1/3, which is the cube root of a. D is a little bit of a trick to it. A couple ways we can do this. One is you could take the cube root of 125, which is 5, and then your answer is going to be the square root of 5. Another way, you can multiply the two roots. The cube root and the square root gives you the 6th root. 3 times 2 is 6. You can also realize that 125 is 5 to the 3rd. So you have the 6th root of 5 to the 3rd. Well, that's 5 to the 3/6 power, reduces to 1/2, and you have the square root of 5. Letter E, even though we've got parentheses here and plus and minus, what's in the parentheses is the same thing, so we can actually combine them. These are like radicals. So we can add the powers. 4/3 plus -1/3 is 3/3, which is 1, and we're just left with 2x minus 1.